Okay, so how do we do free space quantum communication? It's very easy. All we need to do is encode quantum states into optical signals. Seems easy enough. Why photons? Why optical photons? Well, photons have a set of unique properties that actually make them quite promising and a great candidate for encoding quantum signals for communication. Photons have multiple degrees of freedom suitable for quantum encoding. So photons have, for example, their frequency, photons have their polarization, etc. There are different degrees of freedom that we can use to encode our logical quantum states. These photons travel at the speed of light, which is great for communication systems. These optical signals, these photons, can be manipulated with optical components, and optical components are quite mature. You can buy them commercial off the shelf. You'll typically find a whole suite of them in your nearest university lab. But this technology is quite mature in how we can manipulate states of light. Photons are also promising because they are compatible with telecommunications infrastructure. So as we further develop this technology of quantum networking and quantum satellites, we don't want to rip and replace all of the great infrastructure that we spent a lot of time and money on. We don't want to rip and replace with new special quantum fiber. Let's leverage the existing optical fiber and networks in the ground. So we want to be compatible with existing infrastructure here, and photons serve as a great platform for that. Photons operate quite well at both cryogenic temperatures as well as room temperatures, which makes it a promising platform for space deployment. And I like to think of optical photons as sort of the universal language or medium by which quantum platforms can communicate. So there are many different quantum platforms out there. Even in, say, quantum computing, you have superconducting qubits, trapped ion qubits, cold atoms, etc. There are all these different platforms and architectures for implementing, say, a quantum computer, all with different properties. If we wanted different quantum platforms to communicate with each other, we should use optical photons. The reason for that is because they serve as the most promising interface with these separate quantum platforms. So for example, you can have a wavelength of a photon that's resonant, say, with a matter-based system. And so we can begin to explore these interfaces and connect a variety of quantum platforms together. So all of these properties of photons make it a very promising spectrum for encoding quantum states for communication. Okay, so how do we actually do the encoding? There's no one-size-fits-all, no single recipe here for the best encoding. I will say the most popular encoding is polarization encoding. And here we're using what's called the discrete variable encoding. So we're encoding a quantum state into the polarization of a single photon. So if you look at the figure at the top right, here's an example encoding in which we encode the ground state or the zero state of our quantum state into the horizontal polarization of a single photon, and we encode the excited state or the one state into the vertical polarization of a photon. And if we do that, we can, for example, encode superposition states. So this is something that cannot be replicated with any classical system. So for example, if we wanted to prepare a plus state there that you see at the top right, we can encode that in, say, a diagonal polarization of a photon and or the anti-diagonal. So we can leverage superposition and entanglement via photon interference to create multi-qubit states. So this is typically one of the most popular encoding mechanisms. So that's using the polarization degree of freedom of photons, but there are other degrees of freedom that we can use to encode quantum states. So for example, there's what's called time bin encoding, or if you have heard of time bin qubits. This is really using the position of the photon in time as a dimension to encode our quantum state. So depending on when we expect a single photon to arrive at a certain place, that will determine what the photon's state is. So for example, we can say an early arrival is the 0 state and a late arrival is the 1 state. So we can use time as that dimension. We can also use space as another degree of freedom. So there are optical components that can manipulate the path by which a photon will travel in space. So we can use, say, different physical paths in space to encode our states. And we can use what's called presence or absence decoding to detect what kind of state we have. We can also leverage frequency encoding using the spectral band. So for example, here we have linear optical quantum computing, which is a proposal out there for actually using frequency encoded photonic qubits for scalable quantum information processing. So the point is here, there's no right way or single way to properly encode quantum states into photons. There are many levers we can pull. There are many degrees of freedom we can leverage of a photon to encode quantum states. They each have trade-offs. And I'd like to touch on wavelengths a little bit here, because wavelength selection is critical as we're building these space-based quantum communication systems. The wavelength selection is critical because they come with trade-offs, right? So depending on the system we're trying to set up, what are the distances we're talking about between satellites and ground stations, between ground stations on Earth, etc. We have to think about crosstalk as well. So is there other traffic in a nearby wavelength regime that may interfere with my quantum signals? We also have to consider resonance with matter-based systems. So if we want to communicate using these photons to, say, a matter-based quantum system, there are certain wavelengths that are resonant, say, with that type of matter or ensemble. There's also practicality considerations out there, right? What technologies and components are out there that are compatible with a certain wavelength regime, and we have to consider, all the cost factors and form factors as we're deploying on a satellite.